Hi everyone, welcome to today's Webinar Wednesday e-learning session. Today's topic is going to be simulation troubleshooting. My name is Chris Ma. I'm going to be the presenter today. And just to give you an idea of our agenda, what we're going to cover today, really three general topics in simulation that most people will want to go ahead and troubleshoot. There's mesh troubleshooting, there's solver troubleshooting, and then finally results troubleshooting. Let's go ahead and start with the first topic, mesh troubleshooting. Now, if you're watching this video, you've probably seen a couple of these messages before. The main message, or really the only message that you see when meshing and you get an error, is mesh creation failed, and it'll give you a list of one or more parts or one or more features that failed mesh creation. The other message that you might have seen is this message off to the left talking about some bodies interfering and if you want to check. Now, there's really only a couple causes for a mesh failure. The first is interference. If you have parts that are interfering even just slightly, if you're in one of the newer versions of SOLIDWORKS simulation, you're probably going to see this message off to the left that at least two bodies are interfering. Do you want to check for interference? Other older versions of the software won't even give you this message. It'll just go ahead and run, and you'll either get a mesh failure or you won't. The other cause of mesh failure is bad geometry. Now, I see this the most with imported parts. If you're bringing in IGES or step files, even Parasolid files, and you have some bad geometry, maybe some short edges or a bad face somewhere, you can see a mesh failure due to that. Now, probably the biggest reason for mesh failure, the most common, is the fact that you have too coarse of a mesh. And we'll get into how to work with that, but obviously you know that cranking the mesh up so that you have a really fine mesh for your overall assembly is going to just take way too much time to do. So we'll talk about techniques for that. And then finally, the last main cause of mesh failure is a compatible versus an incompatible mesh, and I'll talk about that topic as well. Now, some of the tools that I do use when troubleshooting not just meshes, but using this for the solver as well, you'll see this a little later, I'll talk about it, is interference detection. Now, this tool is actually not in the simulation tool set. It's actually in the assembly tool set, and so anybody, even if you don't have simulation, can use interference detection. And this can be found in the tools menu under interference detection. Also, if you have an assembly open, you can go to the command manager and go to the evaluate tab, and there's going to be a button there for interference detection. Now, I find this is my favorite method for figuring out both interference but also coincidence too. So if you see here, you see this checkbox on the left, treat coincidence as interference. This is a great tool for figuring out, okay, well, if let's say I have a global contact set, and if you know about global contact sets only apply to initially touching faces. So if the faces aren't touching, you're not going to get that global contact set applied to it. And what I often find, not with mesh failures, but with solver failures, is that you might think two faces are touching, and you might see them touching, but really maybe they're offset by 1/1000th of an inch and you won't notice it. Even if it's off by 1/1000th of an inch because it's not touching, you're not going to get the contact set and something's going to fail, probably in the solver. But this is a great way of checking that. The second tool I want to talk about, and this is more in reference to bad geometry, is under Tools Check, and this is at the part level that you can do this. Now, I would highly suggest you use this even if you do go ahead and use that import diagnostics. If you've brought in a imported part, go ahead and use the check tool and see if you have any invalid faces or invalid edges there. And again, if you go into tools at the part level, you'll see this check there, but it also can be found in the evaluate tab as well at the part level. So we've talked so far about geometry issues. You have interference, is a geometry issue, and then you also have bad geometry. Bad imported geometry is another issue. But again, the biggest and probably most common reason for mesh failure is too coarse of a mesh. And you know that with a mesh, if you make it completely coarse, you'll probably get inaccurate results. If you make it too fine, you'll just be sitting there and your solver will run for a really, really long time because you have a lot more information to compute. Now, if you find that your mesh is too coarse, rather than turning up the mesh globally for everything, we do have tools in SOLIDWORKS simulation for localized mesh control. And you can apply this localized mesh control to components, to faces, to edges, and vertices. Now, you could see that using mesh control is ideal for large assemblies with small parts. If you use a global mesh size, what it's going to do is it's going to look at the overall volume of that top level assembly and going to assign sort of an optimal mesh size. You know, when you go to create a mesh, you have that slider that's coarse on the left, fine on the right, and it always starts in the middle. That middle number is always calculated based on the volume of the upper level assembly or the part that you're using. So if you have a large assembly, a large in terms of physical size, and you have a lot of small parts in there, what it's going to do is it's going to find the optimal mesh size in the middle for that large assembly. But then you'll have maybe small flanges or other hardware in there that you want to mesh that the mesh is going to be too coarse for. So that's why we use mesh control for that. The last thing I'm going to talk about before I'm going to go into SOLIDWORKS and show you is the incompatible and compatible mesh. Now, if you go into your component contact, and this is also where you would apply global contact set, you have this option at the bottom. You look on the screen capture to the right. There's compatible and incompatible mesh. Now, the picture I have here is an example of an incompatible mesh. And when I say incompatible, if you look at this small gasket down at the bottom, you can see this is a fine mesh, a relatively fine mesh, compared to what it's attached to, which is a pretty coarse mesh. But you notice that the endpoints or nodes of the coarse mesh element don't coincide with the nodes for the fine mesh. And that's why it's incompatible. If it's a compatible type of mesh, it's going to have a lot more gradual of a transition between the coarse and the fine mesh. You'll see that here it would, for a compatible mesh, you'd have a node endpoint here, and then you'd have a coarse node endpoint attached to it. So for every node, there'd be a node to node touching. Sometimes, if you have a really coarse mesh and you have a really fine mesh right next to each other, SOLIDWORKS is going to have a hard time making a compatible transition between the two. And so sometimes if you switch it to an incompatible mesh type, then it will solve. So with that, let me go ahead and switch into SOLIDWORKS and let's take a look at troubleshooting a mesh. Alright, so what we have here is a pressure vessel model. And what we're going to do is we're simply just going to mesh this straight off the bat and we'll see if there's anything going on. So first I'll go ahead and turn on simulation. And we're just going to go ahead and create a new study here. And first thing we're going to do is we're just going to go ahead and mesh this. We're not going to apply any loads or any fixtures. We're just going to mesh it. And for our mesh parameters, you could see that it's set sort of that optimal mesh level in the middle, and it's decided that it's about 11 inches here. We're going to use a curvature based mesh, and we're just going to go ahead and say, okay, just run this. Okay, so it's telling us right here that we have at least 3 parts that have failed the meshing. So what I like to do, click on this mesh failure diagnostic, and it'll give me a list of what's failed here. So it looks like 3 parts so far. Now what I like to do is I like to actually take a screenshot of this window and so I can actually have it separately, and I can look through and see what I need to add mesh controls to. So what I'll do is I'll just go ahead and use a screen capture tool. I'll use Jing. I'm a fan of Jing. And I'll go ahead and just capture this window here. And I'm just going to keep this on the side just so I have a list here. Let's keep it over here. So now what I'm going to go do is go ahead and go through my list and figure out, okay, which ones are actually the ones failing. So I'm going to look at this head-1, and what I find really nice to do is to come into my feature tree and use this bar up here. And this is actually my search filter. I can come in and type in head-1 right here, and I have that head-1. I'm going to go ahead and open this up. And this is the top dome piece that we have here. And so to figure out what size of mesh that I want to run this at, I'll just go ahead and at the part level create a new study, and then I'm just going to right click and create a mesh here. And I know that because this is an optimal size here, I'm not going to need to mesh this, but just to be sure you can, just go ahead and run the mesh. But really what I want to get at is the number here. And so right here it's about 1.69, 1.7, and so I'll go ahead and use that number. So I can open up something like Notepad if you want to keep an eye on it, and I'll just type in head-1. We'll say 1.693. So I'll get out of this part. I won't save any changes. And then the next one I have is steam outlet nozzle 1. Okay. And do the same thing. Check the mesh number. It's about 0.487 for the steam outlet nozzle. And then for the steam inlet nozzle, let's go ahead and find that. It's about 0.979. Alright, and so now what I want to do is take those numbers that I had and actually apply some mesh control. Now remember, you can apply mesh control to components, faces, edges, and vertices. Now if you're not careful, you might inadvertently add a mesh control to a face when you want to apply it to the entire component. So what I like to do is, again, using this filter here, I'll go and find head-1. I'm going to click on it so it's actually clicking on the component, and then you can come in here and go ahead and apply the mesh control. You can also right click here and apply mesh control as well, and it'll have it already selected here. And what you want to do is then type in the number that we have into this element size here. So let's take a look. We have, this is for the head, it's 1.693. Okay, we'll apply that mesh control. And then for the steam outlet. .487. And then for the steam inlet, let's take a look. 0.979. Alright, and so then what we'll do is we'll go ahead and mesh it with these three mesh controls and see what happens. Oh, looks like we have one more failure. So this is why it's sort of an iterative process, because even though it didn't find this part the first time, after we remesh those individual parts, it did find another one that failed. So I know it's shell 1-1. If you accidentally say OK and you don't bring up the failure diagnostic, it's okay. If you right click on the mesh, you can go to failure diagnostics here and it'll bring that up again. So it's shell 1-1. So I'll go in and I'll do shell 1. Again, open it up. Let's take a look. And it's 6.099. Alright, and then we'll go ahead and run this one more time. I think it was shell 2-1. Let's try that one more time. There we are. .376. All right. Let's actually do this. Let's go ahead and let's modify that last mesh control because I don't think we need that. And what we'll do is we'll pick on this bottom section and we'll do 3.376. And we'll go ahead and mesh this. And 1-1. I think we'll apply one last mesh control. And the only thing I don't like about using this tree is that it doesn't have that filter, so let's mesh it pretty fine just in this case, just so we can go ahead and move on here. Alright, looks like it fully meshed successfully all the different parts that we had. It took a couple tries, but we have 5 mesh controls on this, and you could see here the range. We're talking about from coarse on this flange to more fine on this outer portion to the top dome, and then decently fine on this ring here. So you could see a wide range. We can't just simply use a global, and you can't crank it. It's not necessary to crank it all the way up when you don't need to. So mesh control is definitely a good tool to use for that. Alright, so we've talked about mesh troubleshooting. Let's go into the next section, which is solver troubleshooting. Now really there's 2 primary messages that you get when you have a solver error, and I have a third picture here, and the reason I have a third picture is because this is actually in an older version that I've usually seen it in, and it really is actually the same message as one of the other messages, but it's essentially either you get a matrix singular or indefinite, or you get a model is unstable. And something that I found that I didn't know was that this is actually solver dependent. So the message on the left is talking about the FFE plus solver, the iterative solver. So if you are using the iterative solver, you're only going to see this message for a matrix singular or indefinite, or we'll find out later what that actually means. If you're using the direct sparse solver, you're going to see the message on the right. The model is unstable. Now, the one below it is actually an older one, preconditioner fails to factor, but it's essentially an unrestrained model, and that also comes with the iterative solver. Now, there's a couple reasons why these messages come up. It's usually because there's something in your model that has a rigid body mode. It's moving away from where you want it. Now, usually this is not a problem with fixtures. Most people that, when they're doing a simulation, are pretty good about fixing where they want to fix it so it doesn't move, or how they would fix it in real life. Usually what ends up happening is this is a contact set problem. It's either you didn't apply enough contact sets, individual contact sets, or there's an assumption that you made that there was a global contact set that applied to certain parts that didn't actually get applied. Now, how would you troubleshoot this? Well, again, remember I mentioned interference detection. In this case, for the solver troubleshooting, if you've already passed the mesher phase and the mesh is fine, what I would use interference detection for is, remember that checkbox for treating coincidence as interference. I would use that and check and see, are the faces that I think are touching actually touching? Because oftentimes it'll be a global contact set problem. Another way to troubleshoot this is to use a tool in the static, well, not just the static, but the properties of the study that's called soft springs. And there's a checkbox here in the screenshot that says use soft springs to stabilize the model. Imagine what this is doing is it's putting a whole bunch of foam around your model. I like to think of it as foam. Really, they're little stiffeners or springs that will stabilize your model. Now, I wouldn't necessarily use this for day-to-day analysis and trying to get good numbers, but what I would use it for is a troubleshooting tool. And so think of it as covering your model in foam so it can't really have a rigid body mode, and at least you can see what happens to your model rather than it just erroring out and not giving you any other information. Now, one other thing that I did find is see if it happens in both solvers. If you're trying it in one solver, try it in and it fails, try it in another solver and see if that will actually go through or not. And you might, instead of getting an error, you might get an excessive displacements warning, and from there you can see what's moving or what's going wrong with your model. And then once you've figured out what's going on, you're going to need to add or modify the contact sets that you already have. So now let's switch back into SOLIDWORKS, and I'm going to open up a different model here. So I have this mock-up of a part of an engine, and I have a study already set up that has a pressure on the top. It's being fixed with some fixtures on the bottom, and it's just going to push down on this. Now I'm running the FFE plus solver, and I'm just going to go ahead and run this. And so immediately it comes up with matrix singular or indefinite. And so if I go ahead and say OK, it doesn't give me any other information. I don't know what went wrong with my model. So what I'll do, first thing, you can either try a different solver, and I know for this particular one it'll actually give me an excessive displacement warning, but usually what I'll try next is I'll right click at the top here and go to my properties of my study, and this is where you find that checkbox, use soft spring to stabilize the model. So I'll go ahead and turn this on, and then I'll rerun my study. Now this is that message that I was talking about, excessive displacements. This is a warning. This is not an error message. It's just letting you know there's a lot of movement going around in this model. And you get two options, well technically three. You can say yes, I want to run this with the large displacement flag, no, I don't, or cancel and just stop this study. Now 99% of the time I'm going to say click the no button. The reason for that is really twofold. One, if you click yes, it's going to turn on the large displacement flag, and it's going to take a really long time to run. And usually in static analysis, the large displacement is not what you're actually intending. It's usually something you did wrong, and it's something's flying off into space. The other thing about why I don't click yes is because if you do click yes, and you go ahead and run that study, and it runs to completion, that large displacement flag is now going to be on every time you run that study until you consciously go and turn that off. And a lot of people don't realize this, and so they'll click yes once and forget about it, and then the next time they run that study they'll wonder why it's taking an inordinate amount of time to run. It's because the large displacement flag is still on. So I'll go ahead and click no in this case, and it will finish up, and it will show some movement. And the thing you notice about this also is the deformation scale is 10 to the negative 8. So this is moving a lot, but it has to shrink it down to capture it. And so usually what I'll do is I'll take a stress plot or a displacement plot, doesn't really matter, and I'll right click and animate this. And this is sort of the best way of looking at it and saying, okay, that's not what it should be doing. The connecting rod here should not be passing through to the crankshaft. There's something wrong in here, and that's what's going wrong. So I'll need to modify my study. Now, just as sort of a side note, if you do accidentally hit the yes button for the large displacement flag, to turn it off, you right click your study again up at the top, go to properties, and then this large displacement flag checkbox is here. You want to make sure that's off. So I'll go ahead and turn off soft springs for now. And if we go back to our model and take a look, we can check our interference detection. Calculate, no interferences. But remember, turn on this treat coincidence as interference, and then recalculate. And so we only have one contact set really in this model, and it's a global bonded contact set, meaning that any initially touching faces are going to be bonded together. Now, I intended for this whole bottom section to be bonded as well, but if you look, there's only two coincidents up at the top. That means that if we actually go in here and look, there's actually gaps from here to this sidewall, and also the OD of here and the OD of this inner cylinder. And so there's no touching, they're not going to get the global bonded contact set, and that's why this is passing through. So at that point I would either make a modification of my model to make sure they're touching, or manually add a contact set on those two specific faces. Now, I've been asked this before, if you actually dig down and realize there's actually two different solvers in SOLIDWORKS simulation. But there's really three options. There's the direct sparse, there's the FFE plus, and there is the automatic option. We always recommend, you know what, keep it on the automatic option and it will decide for itself which is the best solver. But just in case you want to know a little bit about it, why there are two of them, there's actually advantages or disadvantages to using one versus the other. So, as sort of general rule, I find that direct sparse is the preferred solver for models that have a lot of contact sets, especially no penetration contact sets. You're going to want to use the direct sparse solver. Not to say that the FFE plus will not work, it's just that direct sparse is the preferred method. Now, FFE plus is preferred for large problems. And when I mean large, I mean lots of components, and it's going to take a long time to run. The reason for that is the direct sparse solver is not as efficient with resources like memory as the FFE plus solver. I've actually run a study that had something like, I'm going to say 12 million degrees of freedom, something like that. With the FFE plus solver, it used about 4 or 5 gigs of memory. With the direct sparse solver, it actually used up all 16 gigs of memory on the machine and then gave me an out of resources error. So just keep that in mind when you're choosing solvers. But again, what we usually recommend is keep it on the automatic. If you don't want to think about it, just keep it on the automatic setting. Now, if you are running into an error besides the ones that I've shown, the matrix singular indefinite, or that your model's unrestrained, try a different solver. Even if you're running the automatic, try a different solver than what was used, and see if you get the same problem. It could be solver related, that for your specific model, for that particular solver, you might run into an error. Now, the last section here is on results troubleshooting, and it's probably a question we get primarily, if not just the error ones. I find a lot of our simulation tech questions have to do with results troubleshooting. And what I mean by results troubleshooting is, why don't my finite element results match real life? Why don't they match my lab data? Why don't they match the field tests that we've done? And so there's a couple things we can look at with that. First thing is, check your materials. You're making an assumption when you're using one of the SOLIDWORKS default materials. Now, if you have a good vendor or a good supplier that has data sheets on the materials that they use, I would highly recommend using a custom material. You make your own material in the SOLIDWORKS library and type in all the mechanical property numbers, your elastic modulus, your Poisson's ratio, yield strength, etc. Now, if you don't have one of these types of sources, what I would recommend is either if you have a textbook, or even if you go onto something like MatWeb. MatWeb has a service. You pay $100 a year, and you can actually directly download materials from their library into SOLIDWORKS. It'll pre-populate with all of the different numbers there, and you can save yourself some typing. But even if you don't use their membership service, you can actually browse and look at the material numbers and type them in yourself. And what's often nice is that for certain materials, they'll actually give a range of on the low side and on the high side, and so you can do sort of a best and worst case scenario for your material properties. Now, the other thing is your study type appropriate? And this more has to do with the mechanical static analysis. Is your model actually yielding, or is it deforming a lot? If so, maybe linear static analysis is not the appropriate module that you want to use. Now, if you're using something like a nonlinear analysis and it's yielding, ask yourself, are you using the correct material model? We have several different material models that are going to be more appropriate than just that linear elastic isotropic material model there. Also, check your fixture assumptions. Now, you can check your loading assumptions and your connections, your bolt connectors and things like that, but your fixture assumptions are really where you're making the largest assumption, and you'll get a big variation in high stresses or stress concentrations. And the last thing to check is, has your solution actually converged? In finite element, you can make a really coarse mesh, you can have it run, and you'll get some numbers, but you could find that your solution is mesh dependent, and that'll be a problem as well. So let's talk about materials. What material are you using? Well, like I mentioned, the best idea is to get a data sheet from your material supplier and make your own custom material. We highly recommend using custom materials because everyone's using a slight variation on the metal or whatever material you're using. If you want to have accurate results that match your lab tests or your field tests, check your materials and make sure the numbers are right first. The other thing that I found, especially on tech support, is if you do make a custom material, beware of the units in your material. I've found that I've had a couple customers who they've had their units set to megapascals and they've typed the number in as if they were typing it in Pascal. So they were 10 to the 6th units off and they couldn't figure out why they had a super stiff model that didn't show any stresses. It's because their elastic modulus was incredibly high. So just make sure if you're in the material library, check your unit system that you're in and make sure megapascals, pascals, if you're in PSI, just make sure the units are right. Now, going back to, is your study type appropriate? With a linear static analysis, you're assuming that the material behaves linearly through its entire range. Now, even if the model has yielded, if you're using that linear static analysis, it's going to still assume a linear stress strain curve even past yield. So, just to show you a picture of this, here's our stress strain curve, and based on empirical data, you're going to see a lot of metals behave in this fashion. You have an elastic region, a yield strength at some point, and then you have a plastic region which is no longer linear. Again, if you're using that linear static solver, it's going to assume that this elastic region goes on forever, even past yield. So you get a straight line all the way up, and so you can see your stress results are going to be significantly off from realistic numbers. Now, in the nonlinear analysis tool, not only do we have the capability to address large deformation problems, but also yield. And so if you are dealing with yield problems, you want to make sure that you're using the right material model. Not only do we just have the linear elastic isotropic model, but we also have a plasticity model, which is what you should be using if you're interested in behavior past yield. We also have a hyperelastic model, viscoelastic model, and so forth. So make sure in the material library that you take a look and you're using the correct material model with the appropriate stress strain curve. Now, how are you fixing it is sort of the next question I ask. Well, these two pictures here, they look pretty similar, but the picture on the left is me actually fixing the top face, whereas the picture on the right is me fixing all the top edges. And this is actually going to make a difference. You can see here that the picture on the right has some red areas right on that corner, sort of stress concentrations right at that corner. Now, if you are actually interested in the area where you're adding an artificial fixture to, you're going to get some weird numbers. And I wouldn't say weird, but you're going to get some high stress numbers right where the fixture is. And so if your area of interest is that area, what I would suggest is actually model that connection rather than just putting a fixed restraint on it. Just model it if you're interested in that area. If it's something where, in this case, let's say we don't care about where the fixture is, we care about that fillet down at the bottom, it's not going to make a big difference if you use a fixture, you actually model that connection. Now, the last topic is my mesh sufficient, or has my solution converged? Now, just because your model meshed does not mean that that mesh is actually sufficient to give you accurate results. Here we actually have three pictures and there's three different runs of the same model with a progressively finer global mesh. I wouldn't suggest doing the bottom picture just because really there should be an area of interest that you should do mesh control on, not just globally make everything fine, because it'll take a really long time and you might not need all of that data. So to check if your mesh is sufficient, The one thing is your solution should not be mesh dependent. So if you mesh it with a coarse mesh, run it, get a number, run it a second time with a finer mesh, and your answers are considerably different, your mesh isn't good enough yet. You should ideally run several iterations of your problem with different size meshes to see if your solution has converged and if you have a good mesh size. Now, SOLIDWORKS actually has built-in adaptive meshing algorithms. We actually have two of them. There's one's called an H-adaptive and another one's called a P-adaptive mesh. And what this will do is we'll actually go in and run your model with whatever standard mesh that you gave it, and it's going to look for areas of high stress. And then it's going to actually refine the mesh in those high stress areas, and what it's doing is it's refining it, rerunning it, and then checking the results. And there's actually a convergence plot that it follows, and what it's doing is it's looking at strain energy and making sure that the strain energy is actually converging. So I actually want to take a little bit of time to talk about these two meshes here. The other nice thing you get besides sort of the automation of running multiple meshing studies is you'll get a convergence graph to show, okay, has my solution converged? In this case, I've plotted the stress for the different runs for that particular bracket. Without the fillet is the graph on the left, and when you don't have a fillet in a corner, what you get is essentially a stress singularity. And that stress singularity, even if you use an adaptive mesh algorithm, you are essentially going to get divergence. You're not going to get a converged solution. You can see here by this graph the stress is just taking off. The finer and finer I mesh it, the higher and higher the stress is going to go. And if you see something like this, you really want to consider putting a fillet in those corners. If it's a corner, put a fillet on it, just round off that corner. And the reason why is in real life there's really no such thing as a perfectly sharp corner. There's always going to be some sort of round to it. And when you put a sharp corner in finite element analysis, or if you do it in the CAD model, you're essentially telling it there's a perfect edge right there. And if you remember, your stress is force over area. As the area basically shrinks to zero, your stress goes to infinity. So the other graph on the right is an example of stress converging. You'll see that it'll start in the beginning and it'll go up for the first 3 runs, and then it'll actually taper out for the last 3. So we know in that case that our stress levels have converged. So let's go ahead and switch to SOLIDWORKS here, and I'm going to bring up that L bracket and show you the adaptive mesh. So this, in this case, this is an L bracket with a fillet in it, and I'm going to just start a study here. And I'm just going to add a fixture at the top, and I'm just going to put a force on this face. It doesn't really matter what force I'm putting on it, just for example's sake. I'm going to put it in the downward direction and put 50 pounds or so. Now, in order to run the adaptive mesher, what you need to do is right click on the study, go to properties, and you go to the second tab here, adaptive mesh. And you have two adaptive mesh methods that you can pick from. There's the H adaptive mesh and the P adaptive mesh. Now, what the H adaptive mesh is doing is it's increasing the number of elements in high stress areas. What the P adaptive mesh does is it actually increases the order of the elements. So the number of elements stays the same, just the order of the element gets higher. Now, I like to think of that, if you want to conceptualize it, that imagine you have a crazy squiggly line, and you're in Excel and you want to do some sort of curve fitting on that crazy squiggly line that has no equation. If you use an H adaptive type of adaptive mesh, think of it as, instead of doing it as curve fitting with one straight line, you'll do it with a bunch of tiny straight lines. And the finer of a line you are, or the smaller of a line you make, the finer of a line fit you'll actually get on that curve. Now what the p-adaptive mesh is imagine instead of having a whole bunch of tiny lines trying to fit that curve, you're having several different lines, but you're actually, instead of having straight lines, which is a linear approximation, you can have second order, third order, fourth order, up to a fifth order element that's going to try and match that curve, is how I like to think of it. So in summary, H-adaptive is more elements, P-adaptive is higher order elements. So in this case, I'm going to use an H-adaptive mesh, and the maximum number of loops that you can do on an H-adaptive in one shot is 5. You can't do more than 5 here. So I'll keep this on 5. I'll keep the target accuracy at 98% here, and just keep that accuracy bias in the middle. I'll go ahead and say OK. And for the mesh, before I actually run this, ideally I would like to run this as coarse as possible. So I'll run all the way to the left, and I'll mesh it, and we get a pretty coarse mesh here. And we're going to go ahead and run this. 1 run, 2 runs, 3 runs, and you can see it's actually the numbers are going up. And if you hit that target accuracy of 98% or higher, it's going to stop. If you don't, you can actually rerun the study, and it's going to take the previous mesh that it just did and then start from there. So in this case, we have a target accuracy above 98%. And if we actually look at our convergence graph, to do that, just right click on your results and go to define adaptive convergence graph. For this, you can graph target accuracy, you can graph stress, displacement, strain energy, or number of nodes. In this case, I'll graph the von Mises stress, and we'll take a look at it. You can see that it's tapered off, and we've converged to some sort of solution up at the top here. Now, I've been asked, okay, well, why don't you look at displacement rather than stress? Well, if we look at displacement, you can see that displacement actually converged after the second or third run here. There's not really much variation, because displacement always, I'm going to say for the most part, converges before stress does. So in that case, we'll go ahead and we'll hide our graph, and we'll show the mesh. And you can see what it did. It actually meshed in the fillet area, which is where the high stresses were, as well as up at the top where the fixtures were. There's a bit finer of a mesh up at the top here. Just as one last note, as a sales plug here, a shameless sales plug, this is our simulation suite that we have for 2012. Just to give you an idea of what's available, if you don't already know, is with the SOLIDWORKS Premium package, you do just get the static analysis and the motion analysis. For the Simulation Professional, which is sort of that light gray box, you get a lot more studies available to you: frequency, thermal, drop test, buckling. And with the Simulation Premium, you'll get everything in Simulation Professional, plus our nonlinear solver, the linear dynamics, which will cover things like harmonic studies, time history studies, as well as random vibration and response spectra. You'll also have the ability in Simulation Premium to define composite layers, if that's something of interest to you. And then, as always, we have our flow simulation package, which is actually a separate license away from the simulation side. We'll have flow simulation, and we also have 2 add-ins that are available. The electronics add-in for electronics cooling, as well as an HVAC or heating, venting, and air conditioning add-on that we can take a look at. Well, if you do have any questions, feel free to give us a call. Our phone number for the US and Canada are listed here, as well as our email. Go ahead and send us an email, support@hawkridgesys.com. And if you haven't already, always take a look at our website, www.hawkridgesys.com. I'd like to thank everybody for attending, and let us know if you have any questions. Take care.